All right, so today we're going to do something called the integral test to help us determine whether or not a series converges or diverges. We start off more or less where we left off last time when we were explaining the definition of what it means for a series to converge. And we also explained the connection between the series, like such as this one, and the area under the curve. There's a clear connection. Every one of these numbers could be represented by some amount of area. And if you make the heights be equal to these values and the widths all make them equal to 1, then each one of these areas is equal to each one of these numbers. And so there's this clear connection between the series and the area under the curve. In fact, it's very, very, very similar to the areas that we've been doing ever since you started doing calculus. The only difference between our discrete sums and our continuous integrals, the only difference picture-wise is these corners. That is the only difference between the discrete version of the versus the continuous version of the same function. That's the only difference, these corners. And so the moral of the story is that sometimes these corners matter and sometimes they don't. And by matter, I mean if you were to add up all these little corner areas, whether or not they amount to something finite or whether or not they could amount to something infinite. And so the area of the little rectangles could be way, way, way different, infinitely different than the area under the curve if these rectangles get out of hand. And so sometimes they don't matter. Sometimes they're just a finite number. And so whatever the areas of the rectangles do, the area under the curve does exactly the same. And so you could think about it this way. You could summarize it this way. If the rectangles are big, whatever that means, then all bets are off. We know nothing. Okay, but if the rectangles, the sum of all the rectangles of all the areas, is some sort of finite or amount, then there's this clear connection between the sum of the function, discrete function. It will behave exactly the same as the integral version of it. So by behaving the same, I mean they will both be either convergent, infinite, they'll amount to something, or they would both be divergent. They both go the same way. Okay, one jumps, the other one jumps. If one jumps into infinity, so does the other one. That's true love right there. That's only if the rectangles are not adding up to much. They have to add up only to a finite number. And we can't always know whether they do or not, but there are some cases where we get lucky and with some simple conditions, we can declare that the corners don't really matter. These rectangles don't matter. And those conditions would be the following. If the function is continuous and positive, and if the function is always going down, monotone, then the corners don't matter. And so the series and the corresponding integral would be the same. Both converge or both diverge. So let's see what that means. Let's take, for example, this problem. Now, I'm going to make a picture of it. Let's make a picture of the function f of x is equal to 1 over x ln of x. If I was to make a picture, put it on a graph or something, you'd see that it looks like this. The larger that the x's get, the more that the function decreases. It never really goes back up. As you move x's bigger and bigger and bigger, this will be bigger and that will be bigger, so the quotient would be smaller. It's clearly monotone. If that doesn't satisfy you, you could also do a first derivative. Check f prime of x, it's always less than 0. That means that from notions from your first calculus class, you know that when the tangent slope is negative, the function is decreasing. So since the tangent slope is always negative, the function is always decreasing. So it has to be monotone. If it was going to go up, it's going down. If it was ever to go up, then at that point it would have positive tangent slopes. It doesn't happen for this one. And so you can either do it by looking at the picture, or you can be a little bit more rigorous and study the first derivative. Or there are other ways, but that's not what I'm interested in at the point. All right, so this one is continuous and it's decreasing. and it's positive for all x's that are bigger than 1. So therefore, once we've checked that, we can conclude that this one behaves the same as the integral from 2 to infinity for 1 over x ln of x dx. They both converge or both diverge. Since this one is easier for me to determine whether or not it's finite, I'm gonna work on this one. I already know they're both going to behave the same. So by proving that this one is finite, I will have proven that this one is almost finite, because this part over here tells me that the corners don't matter. And so here we go. I'll make a u substitution here. U is equal to ln of x. Then du would be 1 over x dx. And this will become integral for 1 over u, and then this will be du. And then I could convert the limits into u limits maybe. When x is infinity, then u is infinity. When x is 2, u is ln of 2. So ln of 2 to infinity. So this becomes ln of u evaluated from infinity to ln of 2. So this becomes ln of infinity minus ln of 2. And that becomes clearly infinity. So therefore this one diverges, which implies that the original one, 1 ln of n, also diverges. So in this case, what I did is I used the integral test to prove that the series diverges. So if I ever got this one, if I ever see this one again in my life, I'll know this is just nonsense. It doesn't even converge. If you add all that up, you get infinity. Okay, so this is the nonsense test. This is divergent nonsense, and we showcase the integral test. Beautiful, right? Maybe should we do one more integral test? How about this one? Let's check the analogous version of this. So f of x is equal to 1 over x to the 3 halves. If I was to plot that, clearly this is the one decreasing, or I could use f prime of x. Since it's always less than 0, I know it's decreasing. It's definitely continuous from 1 to infinity. So we are checking the conditions. So therefore, this guy behaves exactly the same as the integral from 2 to infinity of 1 over x to the 3 halves dx, or 2 to infinity x to the negative 3 halves dx, or x to the negative 1 half divided by negative 1 half. I added 1, I integrated from infinity to 2, which is equal to 1 over square root of infinity times negative 1 half minus minus 1 over negative 1 half times the square root of 2. And that's going to give me 1 over infinity minus 1 over negative 1 half square root of 2. And that's going to give me something finite. So, by the way, I don't really care what that finite number is. Who cares? It's just finite. And because this piece over here is going to 0, obviously. And so that tells me that since I knew that both of these behave the same, they both converge or both diverge, and I should show that this one converges, therefore this one converges. So their logic would go like this. So therefore, the integral from 2 to infinity of 1 over x to the 3 halves dx converges because of all the work here. And then therefore, the summation of all the 1 over n to the 3 halves as n runs from 2 to infinity also converges, because we've established that they behave the same due to meeting these conditions. And that's it. That's the integral test. Beautiful, right? Super nice test. When you have monotone, decreasing, continuous, and positive, you can see that the corners don't matter, and just try to do the integral and use all your skills from previous classes to do that integral. Okay. All right. I think we should keep it short and sweet here. I'm happy with this video. This is the integral test. Come back for more. We'll see you guys.